Hi, this is Dr. B.J. Swaraprasad, Professor of Civil Engineering at G. Pollard Engineering College, Autonomous, Kurnool. So, as part of a series of video lectures on this particular course, Design and Drawing of Hydraulic Structures, now in this present video, I would like to explain the design of tank sluice with tower head. This is the module 3, which all in the previous video we covered some of the important component parts of the structure. Now in this present video, design of tower head and a cistern are to be discussed. Earlier we discussed about the design of sluice, ventway and sluice barrel, etc. Now in this present video, I would like to explain about the tower head and also the cistern and some of the important drawing features also. So before going to discuss this tower head design, the importance of why this tower head is required for any tank. Generally, sluices are the openings to be provided for a tank to supply water or to draw the water from the tank. So without any regulating structure like this tower head, so it is not convenient to supply water regularly and timely distribution. So therefore it is necessary to provide some structure to regulate the flow through the sluice. So one of such type of structure is called tower head. So in this present case, by means of this tower head, we are going to regulate the flow through the sluice. So that's why it is a tower head. The component of this structure is called tower head. Now we will start the design of tower head. Generally, the tower head consists of a masonry well, as shown in that figure, into which the shutter operating arrangements are fixed and can be operated from the slab on the top of the well. Suppose, let me show this. This is a view of a tower head. So it is in the form of a circular well, within which the shutters are to be provided. These shutters are to be operated from the top of the well. So this is called tower head. Generally, these wells are not less than 1.25 meter internal diameter. So that is the size of the tower. It's circular in shape as a well. Its internal diameter should be at least minimum 1.25 meters. And also have their top taken at least 30 centimeter, that is 1 foot above the maximum water level of the tank. So therefore, the top of the tower should be at least 30 centimeters above the maximum water level of the tank. Of course, the bottom of the well rests directly on the foundation concrete of the sluice. So we can see the position of this tower head in the plan also, as it is at the entrance of the sluice barrel. So already in the previous topic we discussed about the design of sluice barrel, for which the foundation concrete also we fixed the level of foundation concrete. So therefore the bottom of this tower head is simply rests directly on the foundation concrete of the sluice barrel. Now coming to the well steening. Steening in the sense walls of the well. The well steening is designed as a thick cylindrical shell to withstand the radial earth pressure acting on the outer surface. Suppose if you imagine a circular well of masonry to regulate the flow through the sluice. So the material of construction is masonry or concrete, whatever it may be. The major external force acting on this component is earth pressure. That is radial earth pressure. In all 360 degrees direction, the earth will present. Therefore, the radial earth pressure is the major external force acting on the well steening. By doing so, the masonry develop hoop compression which shall not exceed the safe limits of the stress for the masonry. So generally, the design has to be done in such a way that due to the external forces acting on this structure, some stresses will develop, internal stresses will develop. These stresses obviously the compression in nature, which shall not exceed the safe limits, permissible limits of the material. So accordingly we have to design the steening. So let us assume a section of masonry well as shown in the figure with the inside diameter of 1.25 meter. Now coming to this diagram, it is very clearly explained. So all the details pertaining to this present problem. Already we have selected one numerical problem for the design of this tank sluice. Accordingly, the dimensions are fixed. See, the bottom of the well is plus 34 meters level. Maximum water level in the present case is plus 38 meters. So therefore, as per the specifications, at least 30 centimeter above the maximum water level, the top should be. So therefore, the top of the well should be plus 38.30 meters. So from this figure, we can easily understand that the total height of the well, that is tower head. So 38.3 meters minus 34 meters. That means it is a 4.3 meter high well has to be provided as per the given data of this present problem. So we can refer the same figure for the entire description and the design of this component. The top of the well is to be at least 30 centimeter above maximum water level. Therefore, we should keep it as at plus 38.30 meters. And the well is checked for the worst condition. So obviously for the design purpose, the critical condition or the worst condition is when well is empty. There is no water in the well, let us imagine. So the well is in empty. So at that case, there is no counterbalanced force acting inside the well. Why? Because on the outside of the well, there is a lateral earth pressure is acting. So what we are doing, we are going to check the stability and safety of the well steening. So therefore, if there is any opposite force is acting within the well, it is somewhat safe. But critical condition is if there is no water in the well or no water or no earth in the well, so this would be the critical condition. Only the external force acting on the well steening is outside radial earth pressure. Now coming to the dimensions, the total height of the well is, as explained earlier, 38.3 minus 34. Therefore 4.3 meters is the total height of the well. Out of this total 4.3 meters, instead of assuming uniform thickness of well steening throughout its height, it is better to assume a thickness of two different thicknesses. Say, let us say 65 centimeters for a certain length, certain height, and 45 centimeters for a further height. So for economic purpose, we have to choose like that only. So in the present case again, so as per the dimensions of the well or height of the well, suppose if you take, this is the total height of the well of 4.3 meters. We are assuming the thickness of the well steening as, for this portion, the bottom portion up to 36.5 meters level, 34 and 36.5. So for a height of 2.5 meter. This 2.5 meter height of the well is, the thickness is 65 centimeters, that is 0.65 meters. And then further the remaining height, that is up to 38.3. 38.3 minus 36.5, that means approximately nearly 1.8 meters. The remaining 1.8 meter height of the well should be having a thickness of 0.45 meters. That means here we are reducing the thickness of the well steening accordingly. So as with respect to the earth pressure acting on the well steening, obviously from bottom of the well, the earth pressure will be maximum. It goes on decreasing. So therefore, the thickness also we can curtail like this. So it is not necessary to provide uniform thickness throughout the height of the well. That's the meaning. That's why in the present case, we assumed the thickness of the well steening as 65 centimeters for a portion of 2.5 meters at the bottom and 45 centimeters for the portion of 1.8 meters at the top. This is for just economical purpose only. That's what here we explained. Instead of assuming uniform thickness of well steening, throughout its height. Assume a thickness of 65 centimeters up to 36.5 meters and 45 centimeters above 8 up to the top, that is 38.3 meters. Now we have to check the hoop compression in the steining of the well at plus 34 meters where the thickness is 65 centimeters, and also at the level plus 36.5 meters where the thickness is 45 centimeters. Since we have two different thicknesses of the well steining, we have to check the hoop compression developed within the well steining at these two levels typically. The maximum radial pressure is due to the earth standing up to the level of 38.3 with a sloping surcharge of 2:1. This also we can observe in the previous diagram. See here, in the left hand side of this diagram, this is the tank bund. So therefore this is completely covered with earth. So therefore, suppose if you consider this portion of this side of the well, the entire height of the well from right from 34 meters to 38.3 meters, it is subjected to earth pressure. So since the tank bund is present on this side, so up to 40 meters height, that is the tank bund top level is 40 meters with slopes of 2:1 side slope. So we have to consider the sloping surcharge with the 2:1 side slopes. So that is the major external force acting on the well steining. I hope it is clear. See here. The maximum radial pressure is due to earth standing up to a level of plus 38.3 meters with a 2:1 sloping surcharge. In order to check the sections of the well at these two levels, that is plus 36.5 meters and plus 34 meters, it is necessary to ascertain the earth pressures that are actually obtaining at these two levels. Now coming to the design of this what you call well steining, that is in the form of a retaining wall. The earth pressures can be computed by any of the methods suggested for design of retaining walls. So this is similar to the design of retaining walls. The same concept here we are going to apply for the design of well steining. Let us imagine of course the well is in a circular shape. Let us imagine a masonry wall as a retaining wall. So whatever the procedure we are following for the design of retaining wall, the same can be applied for this case also. So among various methods, the Rabon's graphical method is more convenient and conveniently can be used for obtaining the earth pressures with a sloping surcharge as in the present case. So therefore, the earth pressure on the wall at the depth of h below the top of the wall is given. This is the standard formula to calculate the radial earth pressure. So you are all aware about this formula, some sort of Rankine's formula. P is equal to C into K into gamma into H. So with this formula or equation, we can say the intensity of earth pressure is directly proportional to H, where H is the depth. Suppose if you want to calculate the earth pressure at the bottom, the depth would be maximum. If you want to determine the earth pressure at the top of the well, the depth is minimum. So like that, two extreme conditions, maximum and minimum, top and bottom, or wherever we require the earth pressure, the corresponding depth from the top should be taken as H. So in this equation, as P is equal to C into K into gamma into H, the most important variable is H only. As H varies, the earth pressure varies. Remaining all the constants, C, K and gamma are the constants. Let me explain about these constants also. Where C is the Rabon's coefficient, which is equal to 1.65 in the present case. So as it is a graphical method, we need to determine the coefficient C from the existing size and shape of the earth bund. So accordingly, we got this value as 1.65, the constant. So that procedure to determine this coefficient C is not explained in this case. So let us consider that is as 1.65 meters. Whereas the K, other constant K is known to you. So K is equal to, as per Rankin's formula, 1 minus sin theta by 1 plus sin theta, where theta is angle of repose. Where theta is angle of repose or internal friction. It depends on the type of soil. For most of the soils, so we are going to assume that theta value as 30 degrees. So by assuming theta is equal to 30 degrees, we will get that the K value as 1 by 3, 0.33. Since 1 minus sin 30 by 1 plus sin 30, sin 30 is 0.5, that is 1 minus 0.5 means 0.5 on numerator, and 1 plus 0.5, that is 1.5 on the denominator. 0.5 by 1.5 means 1 by 3. This is the Rankin's constant K. So C, the Rehabon's coefficient, that is Rehabon's coefficient, that is to be determined from graphical method, which is 1.65 in the present case, whereas K is 1 by 3. For most of the soils, K is like this only, 1 by 3 only. So once by knowing or by assuming these two constants C and K, we can easily calculate the radial earth pressure at different levels. So in the present case, we require this pressure at two different levels. So let us see the earth pressure on the well steining, that is external earth pressure acting on the well at these two levels. One is 34 meters level, another one is 36.5 meter level. See, if you want, you can see again, refer this diagram. So we are going to determine the earth pressure at B, at A. B is the bottom of the well steining. So that is at plus 34.00 meters. Here the earth pressure would be maximum. H is like this. From the top we have to consider the H value. Whereas this 40 minus 34, that 6 meter is the H value for the pressure at B. Now the next critical section is at A, that is 36.5 meter level, where the thickness is changing. So that's why we have to calculate the earth pressure at this level also, that is plus 36.5 meters. So for which the H value would be 40 minus 36.5. So that is 40 minus 36.5, only 3.5 meters only. So like that the H value will vary with respect to tank bund or with respect to top of the well. The H is varying. See here, the earth pressure on the well steining, the first at the level of 34 meters. That means, so bottom of the well, as the total height of the, here the H is considered from the top of the well only. The radial earth pressure, of course it is a sloping surcharge of 2:1 tank bund slope, but we are going to consider up to the top of the well only. The earth existing by the side of the well up to the top of the well only. So therefore the 34 and what you call 38.3 meters. So therefore the H is 4.3 meters only. Is it clear? At the level of 34 meters, the H is from the top of the well, it is 4.3 meters only. Accordingly, we can calculate the earth pressure P as the one is a C coefficient 1.65 and another coefficient K is 1 by 3, just now I explained, and this 2240 as calculated earlier, the 2240 is the unit weight of the saturated earth. As we assumed this value 2240 is the unit weight of saturated earth, gamma. In the equation it is gamma. Say gamma is the unit weight or weight density of saturated earth. So that is 2240 in the present case, and also H is 4.3. Accordingly, you will get the earth pressure at the level of 34 meters as 5291 kg per meter square. You see, this is the intensity of a lateral earth pressure acting at the bottom of the well. Similarly, and the another level, that is at 36.5 meters level, in between top and bottom, at this particular level where the thickness of the well is changing, that's why we have to calculate the earth pressure at this section also. The same equation we are using, only difference you can see. So C is 1.65, K is 1 by 3, and also gamma is 2240 Up to this, it is the same. Only thing is the H is varying. Whereas in the previous case, the H is 4.3 meters. That is the total height of the well from the top. Whereas 1.8 is the point under consideration from the top of the well, which is 1.8 only. Accordingly, the earth pressure value is 2216 kg per meter square only. So like that, you have to calculate the intensity of lateral earth pressures acting at these two sections. One is at 34 meter level, another one is at 36.5 meters level. At these two levels, this is the first one, this is the second one. At these two levels only, we are calculating the lateral earth pressures on the well steining. Now, after calculating the earth pressures acting on the well, we need to check the thickness of the well, the assumed thickness. Already we have been assumed the thickness of the well at two different levels, two different values, 65 centimeters and 45 centimeters, etc. Now what we are doing is, we are just checking the thickness of the well, whether it is safe or not. So accordingly, we should check the hoop stress developed within the well steining, whether it is within the permissible limit of the value or not. That's all. So for which the procedure is like this. The thickness of the well steining should be checked against the hoop compression stresses developed at inner and outer periphery of the well. So we have to check at both the surfaces, inner surface and outer surface of the well steining. Whatever the thickness may be, in other words, inside the well and outside the well, within the well steining, hoop stresses will develop as it is in circular shape. So therefore, we are going to check these hoop stresses developed in the within the well steining at both inside and outside within the limit or not. That is our task. So the hoop compressive stresses developed should be within the permissible limits of the material, that is masonry in the case, which should be less than 9 kg per centimeter square. So this is the permissible value of 9 kg per centimeter square is the permissible value of the hoop compression for masonry. The material is masonry, the nature of the stress is compressive stress only. Its maximum permissible value is 9 kg per centimeter square. So whatever the thickness we assumed, so for this assumed thickness of the well steining, the hoop stress developed should be less than this value only. That's what we are going to check now. So the hoop compression in the well steining is given by a simple formula, F is equal to A minus B by R square. See, observe this formula, hoop compression F, hoop compression stress is given by F is equal to A minus B by R square, where A and B are the constants to be evaluated from the existing boundary conditions. This is another important point. We have to evaluate these constants as per the existing boundary condition, whereas R is the radial distance from the center of the well. With respect to center of the well, we need to measure the distance radially, radial distance. So that's all. So therefore, this hoop compression is affected by the radial distance, inversely proportional, right? A and B are the arbitrary constants. So what are the boundary conditions? Let us consider the boundary conditions for the present case. As already explained, these are the two boundary conditions for the present case. One is the earth pressure acting outside the well. So obviously, completely on the outside of the well, the radial earth pressure is acting. So those intensity of earth pressures are already calculated. So that is for outside case. Whereas in the inside, within the well, if you consider, there is no earth pressure acting inside the well, obviously. And also, since the well is empty, we consider like that, no water in the well. That is the critical condition. Suppose if you assume either water or earth present in the well, so they may exert certain pressure on the surface of the well. So that may balance the external pressure. So, but critical condition is always to be considered like this only. No water in the well and also no earth pressure acting on the inner surface of the well. So therefore, just simply we can say outside and inside the well are the boundary conditions. So with respect to these boundary conditions, now we are going to evaluate the constants A and B in the above equation. That is equation for hoop stress. So hoop stress F is equal to A minus B by R square. That's what is given. So we have to evaluate these two constants from the boundary conditions. Let us consider one by one. The first case, the well ceiling is having two different thicknesses. Already we know. What are the thicknesses? One is 65 centimeters, that is 0.65 meters in the bottom portion, and 45 centimeters, that is 0.45 meter at the top portion. So that's what here it is very clearly mentioned. For the bottom portion, from 34 meters level to 36.5 meters, that is for a height of 2.5 meters, the thickness is assumed as 65 centimeters, that is 0.65 meters. However, for the top portion, that is from 36.5 meters to 38.3 meters level, that is for a height of 1.8 meters, the thickness assumed is 45 centimeters, that is 0.45 meters. These are the dimensions or the thicknesses assumed. So, as in the first case, at the 36.5 meters, let us consider the case 1 as checking the thickness of the well at 36.5 meters level. So see here, the radial distance, as the hoop stress is influenced by the radial distance r and r square. So we need to calculate the radial distance. The radial distance from the center of the well to the outer periphery. To the outer periphery is, as the internal diameter, the diameter of the well is 1.25. So half of the diameter is radius, 1.25 by 2, plus the thickness at that level is 0.45 meters. So therefore 1.075 meter is the radial distance from center of the well to the outer surface of the well at this particular level, 36.5 meters. Is it clear? So this is the most important parameter. So radial distance. We have to calculate this radial distance very carefully to determine the earth pressure or the hoop stress. Okay. Similarly, the radial distance from the center of the well to the inner surface or inner periphery is given by R is equal to same 1.25 by 2. So as inside the well, only the inner diameter divided by 2 is the inner distance, the radial distance from the center to the inner periphery. I hope it is clear. The radial distances for outer periphery as well as inner periphery of the well from the center of the well are 1.075 meters and 0.625 meters respectively. So similarly, outside the well, the radial pressure is already calculated as 2216 kg per meter square, right? And inside the well, there is no water and no earth, therefore P is equal to 0. So these are the boundary conditions. Once again, I will repeat these boundary conditions. So radial distances outside and inside, and pressure acting outside and inside. So with this data or with this information, we have to calculate the hoop stress. So first of all, we have to evaluate the arbitrary constants A and B, and then we can calculate the hoop stress. So this cross section explains the well at this particular level plus 36.50 meters. So radial earth pressure is acting all around the perimeter of the well externally. So the internal diameter of the well is 1.25 meter. The thickness assumed here is 0.45 meters. So accordingly, we calculate the radial distances. So let us continue this procedure. The radial pressure can also be expressed by the following equation. So to evaluate the arbitrary constants A and B, we are going to consider the radial earth pressure, existing radial earth pressure acting, and corresponding boundary conditions. So already we have been calculated the radial earth pressure by Ranking's formula, certain values. So we can also calculate the radial earth pressure other formula given by P is equal to A plus B by R square. This is somewhat similar to the equation for hoop stress. Hoop stress is given by F is equal to A minus B by R square, whereas the earth pressure is also given by P is equal to A plus B by R square. This difference you have to observe carefully. Okay. Ultimately, we are going to calculate the hoop stress, for which we have to use the equation as F is equal to A minus B by R square. But to evaluate these two constants, we are considering these boundary conditions and also this equation. I hope it is clear. There is no confusion or ambiguity. So P is equal to A plus B by R square, where A and B are the constants to be evaluated from the existing boundary conditions. Let it be A and B. What is the first condition? If you consider outside the well, let it be condition number A, condition number 1, A. Outside the well, earth pressure acting at this level is 2216 kg per meter square, for which the radial distance is 1.075 meters. Just now we calculated. By substituting these values of P and R in the above equation, you will get a numerical equation. A plus B by R square is equal to 1.075 whole square. It would be 1.17, which is equal to 2216. So let it be equation 1. Similarly, another condition is inside the well. So if within inside the well there is no pressure, P is equal to 0, whereas the radial distance is 0.625 meters. The same equation if you use, so A plus B by 0.4, that means 0.625 whole square is equal to 0.4, which is equal to 0. Let it be equation 2. So these are the two equations established from the existing boundary conditions. They are outside the well and inside the well. So what is the pressure acting on the outside the well and corresponding radial distance? That related to condition 1. Similarly, for condition 2, the pressure inside the well, simply it is 0 and the corresponding radial distance is 0.625. This is for condition 2. So like that, we can establish two equations from the existing boundary conditions. So by solving these two equations, simple equations, we will get the arbitrary constants A and B like this. So finally, by solving above two equations 1 and 2 from the boundary conditions, we will get the constant A as 3367 and B as minus 1347, minus 1347. Okay, these are the constants A and B already evaluated. So now finally the hoop compression in the inner periphery as well as the outer periphery has to be determined. So simply we have to substitute these constant and the corresponding radial distance. You will get the hoop compressive stress. See here, in case of inner periphery, the F is equal to A minus B by R square. So therefore, which is equal to A is 3367 minus B is minus 1347 divided by R square 0.625 whole square, which would be 7640 kg per meter square. So of course we can convert into kg per centimeter square for our convenience, which is equal to 0.674 kg per centimeter square. Why we are expressing this? Stress in kg per centimeter square means we know the permissible value of this compressive stress of masonry as 9 kg per centimeter square. To verify or to check, it is convenient to express the stress in kg per centimeter square only. So therefore, it is obviously quite less than the permissible value, as the permissible value is 9 kg per centimeter square, whereas we got this value simply 0.674 kg per centimeter square only. It is far less than the permissible value. Similarly, the hoop compression in the outer periphery also to be checked. So that can also be calculated the same procedure. F is equal to A minus B by R square. Only thing is A and B R constants are same. Only the radial distance will vary. Accordingly, the pressure or the compressive stress will also changes. It is 4520 kg per meter square only, which would be equal to 0.452 kg per centimeter square. This is also less than permissible value of the compressive stress of the masonry. So finally, we can conclude that this shows that no tension is developing in the well sealing, as we got both the values positive only. That's why it is compressive stress. Suppose if you got a negative value of this compressive hoop stress, that means that they represent the tensile stress. In the present case, both are positive. There is no tension is developed. So tensile stresses are not developed in the present case. It is safe. And the maximum compressive stress is also within the permissible limits of the masonry. Hence the section assumed is quite safe. So that's what we can check the stability of or the well staining thickness at one particular level. The same procedure is to be adopted for the next case also. As we have two different thicknesses, so the second one is at the level of plus 34 meters. Almost the procedure is the same, just you observe the differences only. Quickly I will go through it. The radial distance for this level also plus 34 meter also, so that is internal diameter divided by 2 plus thickness. This is the difference. In the previous case it is 0.45, now it is 0.65. As we are considering at the bottom 34 meter means the bottom of the well. So where the thickness is 65 centimeters we assumed, so therefore radial distance for the outer periphery is 1.275 meters, whereas the inner surface the radial distance remains same, there is no change. So inner diameter divided by 2, that is 0.625 meters only. There is no change in the radial distance to the inner surface. Only thing is the radial distance to the outer surface is changed like that. And the conditions as usual, the outside well radial earth pressure whose magnitude is 5291 kg per meter square, and inside the well there is no earth and also no water, therefore the P is equal to 0. These are the internal existing conditions. As usual, the earth pressure is also given by the equation P is equal to A plus B by R square. Accordingly, we can establish two more equations. One is from the outside condition, second one is the inside condition. Accordingly, we have two equations 1 and 2, and by solving these two equations we will get another pair of values A and B. A value as 7000 and B value is minus 2800. So by solving the above two equations we will get the constants A and B like that. A is equal to 7000 whereas B is equal to minus 2800. We have to observe the signs also carefully. So accordingly the hoop compression in the inner periphery of the well is given by F is equal to A minus B by R square. By substituting all the values you will get the hoop compression at the inner periphery as 14,000 kg per meter square, which is equal to 1.4 kg per centimeter square, which is also less than the permissible value, that is 9 kg per centimeter square. Next, the hoop compression in the outer periphery of the well is also same equation. Only thing is the distance is changed, radial distance will change. So that would be around 8,700 kg per meter square, which is equal to 0.87 kg per centimeter square. So this is also less than 9 kg per centimeter square. So therefore in both the cases, that means at both levels and also outside and inside, inner periphery and outer periphery of the well staining, the hoop compression developed are within the permissible limits only. This shows that no tension is developing in the well staining and the maximum compressive stress is within the permissible limits. So therefore the assumed section is quite safe. So accordingly we have to check the thickness of the well stainings. The next component is design of cistern. The another important component part of this structure is cistern. Of course, this is the simple component, as a small component only. Cistern means a chamber. A cistern to be provided at the rear of the barrel. If you imagine the entire sluice barrel at the outer end or exit of the sluice barrel, we need to provide the cistern. I will show this cistern location also. See here in this diagram, this exit of the barrel, we need to provide certain component that is called cistern. So see, a cistern has to be provided in the rear of the barrel. The dimensions of the cistern are fixed arbitrarily. There is no specific methodology or procedure to fix the dimension. But to see the earth conditions of the channel and tank bund as shown in the figure, we have to fix the dimensions, right? So according to the existing conditions and the given data, we have to fix arbitrarily the size of the cistern. The main purpose of the cistern is to enable to us the take off more than one channel through separate openings in its side walls. Generally, from a single sluice, tank sluice, we can supply water to one canal. In some cases, it may require to supply water to more than one canal. So in such case, we need to provide the cistern, and we can distribute that water through the cistern only. That's the reason the cistern enables us to take off more than one channel through the separate openings inside the walls. In the present case, in the present problem, only one channel is proposed in the rear, and the width of the opening is kept as the bed width of the channel section. As given in the problem, at the downstream side of the tank bund, so we are going to supply water through this sluice to a single channel only, so whose dimensions also given. So therefore, this opening to be provided to this cistern is single opening only, for which the size of the opening is equal to bed width of the channel. The cistern also functions as a stilling basin. This is another function served by the cistern. It acts as a stilling basin for onrushing waters to the barrel and reduces any possible covers in the channel. So most of the cases, if the velocity of flow in the sluice barrel is high, the scouring may take place. So to reduce the velocity of flow in the sluice barrel, we are providing this cistern, or in other words, the cistern will also serve this purpose. So these are the two major purposes for which the cistern has to be provided. See, this is the diagram of the cistern. The dimensions of the cistern for the present case are 2.5 meters by 4.85 meters. As shown in this figure, the two dimensions like this. In this, there is parallel to the barrel, the dimension of the cistern is 2.5 meter, whereas the perpendicular to the or right angle to this barrel direction, it is 4.85 meter. This cistern has one opening of size 1.25 meters. The opening is provided to the side of the cistern, side wall of the cistern. This 1.25, why you are adopting 1.25 means it is given as the bed width of the channel to which the water has to be supplied. So that's why we have to provide 1.25 meter opening to the side wall of this cistern, whereas the size of the cistern or the dimensions of the cistern are 2.5 meter by 4.85 meters. I hope it is clear regarding the dimensions as well as the position of the cistern. Now coming to design feature, drawing features, let me explain a couple of minutes regarding this drawing. After designing the structure, so far we designed the major component parts of the structure as one is a sluice, then ventway, then sluice barrel, and also tower head, and then cistern. These are the major component parts of this structure. As this title of the structure is Design of Tank Sluice with Tower Head. Design of Tank Sluice with Tower Head. So in the title itself, the major components are covered. Tank sluice with tower head, sluice and sluice barrel, tower head and cistern. These four are the major component parts of the structure. So in this diagram, we can see all the major component parts of the structure. So let me explain. This is in plan. Suppose if you see this plan, the entire longitudinal direction, if you observe, this is the sluice barrel. This portion is called sluice barrel, right? So, and at the entrance of the, approximately at the entrance of the sluice barrel, in the plan we can see this tower head. Or in the longitudinal section, it is very clearly mentioned. This is the longitudinal section. So, which shows the tank bund, elevation of the tank bund, top of the tank bund as 40 meters and bottom of the tank bund, and right hand side of this tank bund, that is towards the tank side, we have this tower head, a circular well. As discussed earlier, it is a circular well. So this is called tower head. In the plan as well as the elevation, we can see the tower head, right? And extreme left, if you see, this is the cistern. This is the cistern. So this diagram will show all the major components of the structure. Of course, some sectional views also given here, like section across the well, section across the barrel, etc. So individually, separately we can observe one by one. This is the plan. So elaborately here we can observe all the details of the plan itself. So plan of the entire structure. What is our structure? Design of tank sluice with tower head. So therefore we can see the sluice barrel and also tower head, cistern, all the components in the plan. This is the just plan only. And similarly longitudinal section. So just a glance go through this longitudinal section. It is very clear that so a tank bund, and on the upstream side of this tank bund we have the tower head. That is, this portion is the tank portion where water is stored here. We are withdrawing the water through this sluice barrel. We are withdrawing the water through this sluice barrel. That's why at this end of the sluice barrel we have this cistern. This is called cistern. So this is the tower head. To regulate the flow in the sluice barrel, we require this tower head. So tower head again consists of shutters, and shutter operating should be done from the top of the well. So these are all the operating things, but as far as the design and drawing is concerned, we should observe the plan as well as the longitudinal section. And next, this is a somewhat section across the well. In a close view of this well, we can see, as already we designed this major component. So the foundation concrete of width 3.2 meters with 60 centimeter thickness of the foundation concrete, and here you can clearly observe the inner dimensions of the well, 1.25 meter diameter, and two sides surrounded by the masonry wall having two different thicknesses. One is 65 centimeter and 45 centimeters thickness. So this is a clear view of section across the well. I hope it is clear. The entire in this video particularly I explained about the design of tower head and also cistern and some of the drawing features only. So with this, module 3 consists of two parts. First part, design of sluice and sluice barrel and also ventway, whereas in part 2 video I explained about the tower head and cistern and drawing features. So therefore part 1 and 2 comes under module 3, that is design and drawing of tank sluice with tower head. So with this we can stop here. Thank you.